Hey everybody, this is your calculus video on 2.6. So now we're talking about limits involving infinity and asymptotes of graphs. We just finished doing continuity. So you have several objectives, as you can see here. It's really 11. So you're probably going to have to do like one or two from each type of problem. Your types of problems are finding limits, limits of rational functions, limits as x approaches either positive or negative infinity, which means to the far right or the far left. So what happens to y when you go far right or far left? Infinite limits, which is when it'd be, either extreme up or down. So again, positive or negative infinity. Graphing simple rational functions. Domains, ranges, and asymptotes. Inventing graphs and functions, which is going to be key. Finding limits when x approaches infinity or negative. And using the formal definitions, oblique asymptotes, and some additional graphing. Okay, so in this one we want to see what happens when x becomes increasingly large, either to the positive side or negative. We further extend the concept of limit to infinite limits. They provide useful symbols for describing the behavior. So like the technical part is it extends or it outgrows all finite bounds. That just means it goes further than all the numbers. So then we are going to compute our limits using the same type inequality we did before. The difference between these two were there was an m and this one was an n, based on if you're on the left or on the right. So this one says x approaches infinity, this one negative. And then if they are equal, then the limit exists. I'll show you page 84. On 84, we're talking about 1 over x. And as it approaches negative infinity from the left, it's approaching 0. And approaching positive infinity on the right, it's also approaching 0. Basically, a lot of your notes are technical because I basically just typed what was in the book, especially these little boxes and theorems like those. Okay, so now we're going to talk about limit of infinity of rational functions. So if the degree are equal, then you want to divide by the highest power, and that will help you tell what your horizontal asymptote is. An oblique asymptote is when its degree is higher in the numerator than the denominator. It's not the same as a parabolic asymptote, which is 2 greater. By the way, you may remember going back to pre-cal, if your degree was lower in your denominator, then it'd be called proper, and it'd be y equals 0, which is the x-axis. Otherwise, if your ratio, like if you have x squared here and x squared here, then you're going to do 5 over 3. So that's your horizontal. So a little bit of this relates to pre-cal. Here we're talking a little bit about infinite limits. Here I'm abbreviating DNE for does not exist. And again, you can read through all the technical part. But we say that f of x approaches infinity when x is c, and write that the limit equal infinity if for every positive number b, there's a corresponding delta when f of x is greater than b. And then on this end, we say for every negative number, there's one less than negative b. And then we're going to talk about vertical asymptotes, and then dominant terms. So after doing long division, rewrite as linear plus a remainder, or maybe you have quadratic plus a remainder. They help us predict a function's behavior, and the linear dominates and the remainder does when it's undefined. Okay, so let's get into these. So for the first one, you have this graph. It's kind of an unusual function. It says determine the limit, and in this case we're talking about 4. And so you go to 4, go up, and that's at the first mark. Now what you got to watch out for sometimes is the scale, because the x scale on here is 1, 2, 3, 4, 5, so forth. But the y scale is not the same. You go 2, 4, 6, 8, 10, 12, etc. So be careful about that, because I can see some people saying it's 2. Saying it's 1, not 2. So be careful again. Now, pay attention to the y scale. Pay attention to whether you're doing plus or minus, because on this one it means 1 plus, which is the right, like 1.001, and this one's 1 minus, which is like 0.999. So when we're looking at 1 from the right, it's zeroing in on this part halfway between, which is -1. And on the left end, when we're getting closer and closer to 1, it jumps up here, which is 3. So again, those were halfway between. Halfway between y values. And since our scale was 2, then it ended up just being an integer, or a whole number. Now, for this one, they want you to do the limit as x approaches 1, and since it was different numbers, then it does not exist. And it's also not negative infinity or positive, because one time it was -1, the other time was 3. So now on E, we're looking from the right. So think -4 well, it's the right side. So -3.999. And on the left side, which is -4.001. So on the right side of -4, it's up. And -4 from the left is also up, because basically at -4 it was like that and that. So both of these in my case were the same. And since they were equivalent, then this is infinity. And this is exactly what an infinite limit is. So this is an example of an infinite limit. Now on 0 from the right, that'd be like 0.001, and from the left it'd be like negative 0.999. 0 from the right is up, and 0 from the left is down. So if it's up, it's positive infinity. If it's down, it's negative. And because they were different directions, then it would be this little part that's kind of cut off, that it does not exist. D and E does not exist. And then it looks like the next one on the paper is K. And on K, we want the limit as X approaches the right and the left. So on the far right, it's just barely dipping down. So as X approaches infinity, Y approaches negative 1. And this one is as X approaches negative infinity, Y approaches negative 1. And so both of those were negative 1s. So that did have a number of parts, but they're pretty straightforward as long as you pay attention to the scale. Now on this one, we basically want to graph it and look at the right and the left. So a lot of these I think are just going to require using your calculator. We want pi minus 24 over x squared. Okay, so on the far right, it's approaching a certain number. If I go to the table, it looks like it's approaching 3, but if you look even closer, it went past 3, which is not right for your answer to be 3. Now it's kind of like slowing down. What you can do is go to your table settings and start your table at 1000. Now you can see, oh, that's 3.14156. So that's pretty close to pi. So set your table start equal to 1000, and then y equal 3.14156. 6. I'm so used to writing 9 because that's the actual number. So it's close to pi, 3.14159. If you don't remember the actual value of it, it's fine. Just go here, go to the pi button, do Control Enter, and there it is. Okay, now we want to go back to where we were, so I'm going to go back to the current document, and I'm going to change this table start. Whoops, I just did the wrong thing. Go to this table setting, make it -1000, and that's still the same positive pi value. So notice both of these are up to pi. So that's just from the graph. On this one, cosine 9x. Again, make sure you're in radian mode but I just noticed I did cosecant on accident. So cosine 9x. Now we want all of that to be divided by 3x. We don't want to do 9x divided by 3x accidentally. We want the whole thing divided by 3x. So make sure you do parentheses around it, and then also do parentheses that way. So what I'm actually typing is parentheses cosine 9x divided by parentheses 3x. That way I'll make sure that it shows up just like what we want. Now it is kind of interesting. Kind of looks like a heartbeat graph a little bit, just a little. And you can see that we're hovering around 0. Well, this one's asking about the left side, and it's 0. So maybe somebody's heart is being shocked into rhythm, and the scale is not like appropriate, like it's going to bump up again, hopefully. So, okay, on this one, we're going to want to graph it. And so remember, we want to do this and then that. And you use your little slash for the division. Oops, looks curved. Nine x up arrow 4 plus 8 divide by parentheses x to the 4th minus x squared plus x plus 9. And we want what's happening on the right and on the left. So on the right, it's going up to a certain value. I can't see where, because at this point it kind of looks like it's a parabola. But if we use our knowledge of what we said a little bit ago, we have 9x to the 4th, and then this is x to the 4th. And so if you do your ratio, that'll give you your numbers. Or you can graph and change your window. So I'm going to make this one like 20. And now you can see what happens. So it's basically here, then it dips, and then here. Well, it should be equal heights. Oh well. It's as good as I got it. It's right there. Okay, and so both of these are 9s. If you want to look in your table, there it actually went above 9, and now it's coming back down. That's a little interesting. But nevertheless, it really is approaching 9. This time it went above 9, then below, and close to 9. So if we actually just zoom in, you can kind of see a better picture. So that's what's happening here. You don't have to do the maximum, but I'm just showing you it has one. Okay. And then on this end it was 9 also. The easiest way though on that one was just to use your ratio. because that's your horizontal asymptote. Horizontal asymptote y equal 9. Okay, now this one, this is the third root or cube root. And we want when it approaches infinity, which is the right. Do n to the x. Then we have the third root. Gotta do a double parenthesis around this. Now it's dipping down. First, let's make sure we type it right. Okay, and we did. And then there's your answer. Now, I'm not going to say it's always going to work like this, because things can. Oh, well, right there. Actually can. That one simplifies to the cube root of 64 x to the fourth divided by x to the fourth, and then we do the cube root of 64 is 4, because 4 to the third power equals 64, because that's like 16 times 4. So the highest power is what matters, and you got to do the cube root of that. Now, if you're using your table, that's fine. It's close to 4 right there. And again, we can change our table start to 1,000 if we wanted to. On this one, we want negative infinity, so it's the left. You've got to have some nested parentheses on these. So that's your entire numerator. And now my entire denominator is x squared plus 4x. And then both the numerator and the denominator are raised to the 7th power. So like that. Okay. And that just looks like somebody snow skiing to me a little bit. And so you want where it's negative. Well, at this point it's up, but I don't have a clear picture of when it's like far out. So let's go to the table, start our table at about negative 1,000. So like on several of these, could use x equal negative 1,000 for negative infinity, and x equal 1,000 for positive infinity, just to give us a clear picture. Now, would it be better if you put even more zeros? Yeah, but you don't really have to. So I'm changing this like that, and now I can see it's negative 1 something. Now what we have to watch out for is if there's an e, but I can't tell. Yeah, I found it. There's the e to the 42. Be careful. this was negative 1.0284, and then e to the 42. And that indicates negative infinity, which is down. So what I had to do is like get my cursor inside here and type to the arrow to the right. Now, if you'd rather be a visual person instead of an analytical or technical person that way, you could just change your window. First, I want to get rid of this table as inside that table. Now, if I want this to be like negative 1,000, can't see it good. Menu 4A. Now I can. So we could do it visually. So you could set X minimum, which is the left, equal to negative 1,000. Then do menu 4A, which is like zoom fit. And you see what happened. Okay, on this one we're paying attention to where it's 0 from the left. One divide by parentheses 6x. It looks like that. And so to the left of 0 it's down. Looks like that. And that was a bonus. So limit 0 from the right is positive infinity. Now we have a linear function. And I would imagine on this one that whatever number this is the number they're going to use. In this case we want 6 minus, so that's 5.999. Now what that function looks like is basically if we say this is 6, that's your asymptote based on our situation. X equals 6 is your vertical asymptote, y equals 0 is our horizontal asymptote, and this was trucking down like that and like that. Now when we're looking at 6 from the left, it's down. Look there, it's down. So negative infinity. Okay, now we have more of the same type, and you're just paying attention to whether it's 1 from the right or left or negative 1 from the right or left. So we basically just need to graph these. It's not surprising that you have to graph it. Okay, that one looks like that. There, negative 1, there, 1. Okay, so 1 from the right is up. 1 from the left is down. And this is negative 1 from the right, that's down. And from the left is up. What's up? Okay, now on this one, use x instead of t. And this part's the actual function, and this is kind of like the piecewise part. Like you're doing 0 from the right and 0 from the left. Fifth root. Like that. So on the left it's down, and on the right it's up. Again, you can do many 4a if you want. Okay, now this one you work like you did in pre-cal. So the first thing is they want the horizontal asymptote, so you do your ratio x over x, and so you get 1. For the vertical asymptote, set your denominator equal to 0, so x plus 5 equals 0, so you get -5. And then you do your graph, which would be this one, because you go to the -5. That's the only one that had the -5 with the horizontal at 1. Now on this one we want our domain and range. Now what I can tell you about this one is when we do our ratio for the horizontal asymptote, you're going to get 1. And when you do your denominator equal to 0, x cubed minus 1 equals 0, x cubed is 1, and so x is 1. It's not plus or minus because it's the third root, not the second root. But that's just a little extra. Here we have x to the third power, divide by parentheses, x to the third power minus 1. So it does a little like hiccup, so to speak, right there. So your domain looks like everything except for the vertical asymptote at 1. So this is like all reals, x not 1. And so remember, when you have a vertical asymptote, use parentheses, not brackets. And for the range, it was all good except for at the 1. So this was all reals, y not 1, from the horizontal asymptote. So it's almost like it slipped and then it went further. Now on this one, the definition says f of 0 is 2, which means the ordered pair is 0, 2. So look at all the ones with a dot at 2. So right there you can rule out 2 choices based on the first part. Now, if we want the limit from the left and right to both be 2, this is 2, this is -2. This one looks like 1, and this one looks like 3. So right there, you know your answer. But you can also look at 0, it wants 4 from the right, and then 0 from the left. So that is the conditions. All conditions are met. This one, you have your limit from both the left and right is 0. And your number focused on here is 2. Like 2 from the left is up, 2 from the right is also up. So what I'm looking at is when it gets to 2, we're going to be like that and like that. But we also have on the far right it's 0. Now when both are up, then it's going to be like 1 over the function squared. If it's like this, it's 1 over x. If it's like this, that's negative 1 over x. And if you have both like this, it's negative something over x squared. So what we have is this one in my case, and that graph is this one. Now notice they're only showing from 0 to 4 in my case, but we center it around x equal 2 and it's up. Now on this one, boy, that hint's going to be terrible. It says multiplying and dividing by the conjugate. There's got to be a better way in this problem. What about if we just say the limit of plug in infinity? Infinity plus 9 is still infinity. This is my thought process. And then the square root of infinity is still infinity. And same thing on the other side. Infinity plus 25 is infinity. So anyway, you end up with infinity minus infinity is 0. So that's how you can think about it algebraically. Now, if you want to graph it, the square root x plus 9 minus the square root x plus 25. So it's starting over here at negative 9 and then it's going to the right. I want to see what's happening at negative 50. Well, this is negative 50. Okay, nothing. Okay, so it's restricting your domain to this end. Restricted the domain to x greater than or equal to negative 9, even though this part was x greater than or equal to negative 25. It's kind of like when we were doing our composite functions with f circle g and g circle f, where if it's not defined for this part, it can't be defined for this part. And then let's wait for that to come into focus. Okay, we're going on the right side. So if we do our, well, there's a few different ways. We do our table setting to make x max 1,000 or 10,000, I guess, then you can see that 0. Set x max equal to 10,000. Or you could set your table start equal to 1,000. That's the approach we've been doing. So it just depends on if you want to look at the table or graph. So table settings, start your table at 1,000. And we're pretty close to 0. And if you want to be sure, then go to 10,000. Just add extra zeros. It doesn't matter how many. Okay, so that's number 15. And then our last one is a paragraph multiple choice type question. They want you to graph this, which I'm sure you can do. Is this. X divided by parentheses square root 1 minus x squared. So it kind of looks like that, which is that. Then it wants you to explain the relationship, and aren't you glad you don't have to write this and then it's multiple choice? Yeah. So what we're looking at is this one. As x approaches 1, it's positive infinity, and in negative 1, it's left. At 1, it indicates positive infinity, and at negative 1, it indicates negative infinity because it's down. It does approach the vertical asymptote. Okay, that does it. I hope you all have a good day. Bye.